Welcome back to Learning Image Analysis. Our topic today is highlighting desired features in your image. So the image that we'll be looking at here is one of a wound healing assay. So the researchers will take some cells and grow them until they're uniformly covering the surface of the dish. Then they'll remove cells from the middle. And the purpose of this is to measure how well these cells can move. So they'll migrate in to fill in this wound. And then you can look over time and see this wound close. So of course, from a single image, what you want to get is the width of this wound. Now this isn't as straightforward as it seems, mainly because the border of the cells in the wound can get irregular as they move in. They don't all form a nice straight line to march into the wound. So when we figure out how to measure the width, we have to come up with a method that's able to accommodate that. Our learning objectives are recognizing features in an image that can be targeted with filters. So what you'll see here is that this image has the same issue we've seen in some of our previous ones, where the left side is illuminated brightly and the right side is a little bit dim. So we're going to use some pre-processing filters to adjust that to highlight the features in the image. Then we'll need to do some compensating for those filter side effects. And lastly, we'll talk about checking your measurements once we've gotten our segmentation, making sure the measurements are accurate. So looking at this image, of course, we have this left to right variation in shading, which tells us that we can't use a simple basic threshold to try to find these cells. Even though we might want to use a basic threshold to just highlight all these light outlines, or to fill in the dark cells, which are darker than the things around them, we can't simply do that just like this. Right? We start to fill in the wound here on the right before we're really fully selecting the cells on the left. So we used in the past the adaptive threshold in order to fix this. So say we have here our cells that we select, just like this. Remember, the adaptive threshold looks at just a local window and picks cells, or excuse me, picks pixels that are above or below a certain percentage of all the pixels in that window. So it doesn't care that this side of the image is darker or brighter than this side of the image. And this actually works pretty well. We can find all the dark areas like this. And say we wanted to find light areas as well. So not all the cells are dark on the outside, some of them are light. So we could combine these two, a light selection and a dark selection. So if I save away our dark selection and then do a light selection, till we have most of, it looks like these cells highlighted, just like that. Right? And then we can sum these two together. Take the union. Right now we're finding both the light and the dark, and they're unioned together. And we're going to do some cleanup. If we dilate this up, say 10, then erode away, 15, and then bring it back to where it's supposed to be, 5. Now we can just find this wound first by rejecting all the little features. So if we want to reject anything that's tiny, so these, say we set a cutoff of 2000. to reject all the things in the middle that were found. And then we can reject holes as well. So these guys here, inside the segmentation, are a couple thousand. This guy is 700,000, the wound in the middle. So if we set our cutoff at 100,000, and here we have our wounds selected. Now, something to think about is that these adaptive thresholds, they're very fast, but they're not instant. Okay? So for each pixel in the image, we have to take a 30 pixel window around it to calculate the statistic that we need to know, well, are we above or below 91% of that value? And so when you start getting large images, say 300 megabyte images, and you start having to do larger and larger windows, they start to take up a lot of time. Plus we have to do them twice. We have to do a dark selection and a light selection. It'd be nice if we could just get some sort of method that is able to select both at the same time and not require multiple passes. So let's start over. And we'll try to attack this situation with our image filters. So a couple that I'll show at the beginning are our bright texture and dark texture. You might know these as top hat and bottom hat. Those are some of the more traditional names for them. So if we start with our dark texture, what it'll do is take a window size and it'll highlight features that are below that window. So we're trying to pick out small features. With a window size of 3, we find these tiny small pieces here. And we start to get some of the outline stuff in our cells. If we turn our window size all the way up to 27, here we're finding really big dark features. So we're finding whole cells, we're finding whole space in between bright highlights on cells. Okay. So that's a dark texture. And then we can do just a basic threshold of this. Say something like that. And then we could do the same cleaning that we did before. But the issue with this is the same that we had with the adaptive threshold. It's finding dark features, but it's not always accurately finding the bright edges. So perhaps you want to find the bright of this particular cell. Okay. For the purposes of this assay, that little bit of error isn't going to be an issue, but for the sake of argument, say you had an experiment where that level of accuracy was necessary. What could you do? Well, what we could do is pair our dark texture with a bright texture. So say we take our dark texture, save it away, call back the original, and now do a bright texture. So this will find all the bright stuff. So it'll find all these bright outlines. Okay. And if we add the bright texture and the dark texture together, we get this. So here we have the wound is still very dark, and the cells have a lot of brightness to them. And we can take a basic threshold here to find the wound. And you notice that the image is also a lot cleaner when you start combining filters. A lot of random noise gets evened out. But we're kind of back where we started with the adaptive threshold. Now we have 5 steps to get to an image that can be segmented. What we'd really like is to have a filter that we'll find both light and dark features. We'll highlight both light and dark features. That way we don't need to worry about multiple steps and adding and stuff. So let's start over again. And there are filters that do that. I'll show one right here, is just a standard deviation filter. So what this will do, again, it'll take a window around each pixel, and it calculates the standard deviation. The standard deviation is a measure of how spread out the values in that window are. And so we'll have both light and dark features producing signal. It's like that. And now in one step, we've gotten to an image that can be basic segmented and be finding both the light and the dark features. And another filter that does this is our entropy filter. So the entropy filter is a little bit different than standard deviation. It calculates the randomness in the image. So we can give a measurement of how random the pixel values are. And so if we do a basic threshold, we'll get a nice look at this nice histogram here. Set a value right about 100. And here we are. Our wound in the middle is found. Now, you always want to be aware of the side effects of these filters. So because we have a window size of 25, this entropy of our cells here creeps out into the wound a bit. So once you've got your image, or excuse me, once you've got your segmentation, you need to adjust that. So that's what we'll do, is we'll dilate by half the size of that window. So if we dilate by 12.5 pixels, that will restore our boundary to where it's supposed to be. And now we can just do some quick cleanup. Reject features. Let's do little measurements here. Again, we're about 700,000 for the wound and a couple of thousand for these pieces. So let's set our cutoff at 100,000. Yep. And we've got some of these holes in the middle that we can fill up just like that. And this will be our wound layer. So now let's measure the thickness of this wound. And we'll start, say, with our measure local thickness tool, which will take the thickness of each pixel here in the image. Specifically, it'll take the thickness along the skeleton of the image. So if we start here and look at our measurements, and we'll say, oh no, this isn't what I expected. We've got lots of thickness here around about 50 pixels, right? And the corners here are very thin. And that's because our skeleton goes into these corners. And that's not what we want. We want to just measure the thickness along this center line. So if we use a smooth skeleton, well, we'll get much closer to what we want, but not exact. Why is the skeleton branching here? Right? This isn't exactly what we want. We don't want to see this branching. We want to see just a single line across. And this is why you always check your measurements and make sure they make sense. What we'll see is this tiny little piece that didn't get found. Okay? So that's we need to go back and fix that. Okay, so what we'll do is, rather than doing the fill all holes, we'll just do a reject features based on area, reject holes. say if we set a 2000 for them. Okay. And that'll take this piece away. Okay. And set our layer here on reject features. Now if we perform our measurement, thickness with a smooth skeleton, it's a nice straight line across. And we'll get a measurement here, a mean of 466. But something to notice is that this particular measurement isn't the most accurate. So you always want to know how your measurements are being calculated. In this case, what MIPAR will do is take each pixel of the skeleton and fit the largest circle it can around that pixel until the circle goes outside the feature. So from here, we can fit a circle to this point. But this distance here is less than this distance here. So this distance to this point is less than the distance up to the top. So we're getting a slightly lower thickness measurement than we actually want. So this 466 isn't exactly the right number. So how do we fix this? Well, one thing that we can do is get the average height of this wound. And we'll do that by using our feature measurements. We're going to find the area, and we're going to find the length in the x direction. So that will give us this x length and the area, and we can then divide the area by the length to get the average y height. So if we add this to our recipe, here's our two numbers, and plug them into our calculator, and we'll get a pixel height of 530. Okay, a fair bit larger than what our thickness tool measured. So this is a situation where you might need to do some post-processing of your data. So you measure all the images in your set and then run them through a Python script or something. In batch, MIPAR can save all these measurements to a text file. You can simply process through them and generate an average y height. And then that would be a measurement that more accurately tracks all the irregularities in the surface of this wound. And that's been our lesson on highlighting desired features in your image. Next week we'll still be on this same topic, but we'll talk about combining two different filters that each have their own side effects, and how you can use different filters to compensate for each other. So I'll see you then.